Okay, thanks for starting the recording. Okay, so well, let's back up a little bit and see how work and energy are actually related. And I usually do the basic level, but since we discussed that problem early on, I think we can do better than that. So let's, so derivation of work energy theorem. And the type of energy that's applicable here is actually kinetic energy. So sometimes you may see work kinetic energy theorem. Oops. Theorem. So imagine a particle that's subject to a force. We can do it in 1D for now, but it actually works as well in 2 and 3D. We have a force, let's say constant force for now, that actually doesn't have to be constant. Force that acts on the particle, certain position. And then, yeah, we don't officially know momentum yet, so we'll just talk about velocity. What we know from Newton's second law is that, and this is the only force, so this F of x equals ma. Or let me rewrite it this way, and I'm going to swap the sides of the equation. So m dv dt equals f of x. So this f changes velocity, then the particle moves. It's a different position now. That means it's a different force. So you have to plug it back into the equation, find a different change of velocity, different displacement, and so on. So what you can do here is to say you have this x of t, the position as a function of time. Then you can rewrite dv dt as let me, don't want it to look too mumbo jumbo-ish. So let me actually rewrite this one more time first. So I'm going to multiply everything by dt. So I have mdv equal f of x dt. So I cannot really integrate because this is a function of x and this is a dt. So one way to do it is to actually express x of t explicitly and plug in here. Then this will be a function of time that you can integrate. But there is a better way to do this. So a better way to do it is the following. We're going to do, use the fact that v equals dx dt. And you can think of v is also a function of x. Some position you have some velocity. Then dt, I want to do from here is this. dt equals dx over v. Okay? So this is dx over v. And then you can multiply by v both sides. So what you have on the left is this. mv dv equal f of x dx. Does this make sense? Now things should be clear. Now I can integrate. Everything is a function of x on the on the right hand side. So I can integrate from some x initial to x final. This I integrate from v initial to v final. That correspond to these x's. Are you with me so far, folks? Okay, then what we got here is the work done from initial to final by this force. Just the definition of work. What do we have on the right hand side? Oh, left hand side.
Wait, how did you go from MV/dV to Fx dx? What was the thing you did?
Say it again.
Can you re-explain how you go from MV/dV to F of force with respect to dx?
You mean here? In which line?
Oh, mdv dt. Oh, then you just multiply by dt. Okay.
Yes, yes. Here I multiply by dt. So I get this. Express dt as dx over v. Then multiply by v. Okay. So this is all you got on the right hand side. And then on the left hand side, you have this combo. And notice, it's like separation of variables. People who did rocket science with me in the spring would know what that is. If not, that's fine too. So on the right hand side, you have things that only depend on x, so you can integrate over x. You can say you integrate from initial to final. Then integration of x means you integrate from x initial to x final. On the left hand side, you also integrate from initial to final, but the variable of integration is v. So I'm putting this integral from v initial to v final. But it's the same, like simultaneous integration, okay? But this integral is very easy to compute. What is it?
One half mv squared.
But that's not the end, right? It's 1/2 mv squared.
Oh, plus sorry, minus. Yeah, evaluated from vi to vf. So 1/2 mvf squared minus 1/2 mvi squared.
Okay, so 1/2 mvf squared minus 1/2 mv initial squared equal work from initial to final. Or what is this?
Kinetic energy at time, at whatever time v final is. Yeah.
Okay, yeah. So this is the statement of the theorem. Yeah, we'll say wet for brevity. That is really this. Delta K equals work from initial to final. Sometimes we skip this as well. So there are two ways to read this. I'm going to probably put it in text. If the force does work on an object, it changes kinetic energy of the object, right? But there is another way to read this, more in the spirit of the definition of energy. Remember, energy is the ability to do work. So, like I discussed that bowling ball, the bowling ball or object in general can do work by spending its kinetic energy. Make sense? The only subtlety between these two interpretations is the sign. So we have to distinguish, and it will become actually more important in electricity or your chemistry classes, perhaps. We need to distinguish between the work done by the object on the outside environment versus work done on the object by the environment or external agents. Does that make sense? So what we did here in all this consideration, we considered an external agent that did work on the object. But if an object does work on the environment, you have to put a negative sign, because if delta K is negative, right, that means object spent energy, the work it does is actually positive. And one key example here is thermal engine. And somehow folks first encountered that in chemistry for some reason. So the gas in that engine, internal combustion engine, expands. It does work, right? It does positive work, but it does that work because it spends its own internal energy, which is really a bunch of kinetic energies, combined kinetic energy of all particles. Is that clear? So that thing you have to be careful about. Most of the time, at least in mechanics, we'll only consider work on the object by external agents. Okay, so this is how work energy theorem comes about. Very simple, very simply stated. The only thing is that you really need to carefully set up initial, final, and understand what's hidden inside this and this. So let's understand how potential energy comes about. And I want to consider some really basic example. Say a ball falls down from some height and hits the ground. Say H. I can pose it as a problem. I can say, okay, I'm dropping the ball from this height. What is the final velocity? But you really know the answer, right? I can actually put it up somewhere. So the point is actually consider something interesting: the transition from one object thing or one object consideration transition to system consideration. So first, let's consider the situation from the wet perspective. So what does wet would say? Delta K equals work. Now, what work? What is doing work on the ball here?
Work done by gravity.
Yep. So work done by gravity. So I'm gonna label this. Say work done by gravity. And this is the only force that does work here, right? So it's very easy. It's a constant force. If it's a constant force, we can compute work by simply doing force times displacement. Displacement is h, but we have to be careful with the sign. So I'm gonna actually put a coordinate system here. Oops. To put it. Y and label y initial, y final. Excuse me for a second. H equals y initial minus y final. So The work done by gravity is simply force of gravity times displacement. K is K final minus K initial. So I put, actually, I don't have to expand it. Just keep it this way. K final minus K initial is equal mg y initial minus y final. Okay. Now I'm going to distribute this and write mg y minus mg final. Okay. Again, I'm not doing something sophisticated, just mathematical rearrangements. But conceptually, I'm actually doing something important. So I'm going to collect all initials on the right-hand side and all the finals on the left-hand side. Okay. So now look at this. Clearly, again, we know what it is, but let's pretend we don't know what this combo is. What can we tell about this combo? This combo has units of joules, right? Just because this is joules, we must be adding joules, okay? Joules to joules. So this is some kind of energy. And if you look at it, this is exactly the same combo on the right and on the left, except for this is final and this is initial. So if we say that this is, if we define UG as MGY, then we have, we can also define the total energy, total mechanical energy is K plus UG and then this equation becomes simply the statement of conservation of total mechanical energy. Okay, so let me summarize. Mathematically, things were pretty trivial. Conceptually, we switched from a single object okay, the ball, to a system, two-body system that has an interaction, gravitational interaction between the ball and the Earth. Okay, one more way to rewrite the same thing is this. Delta E equals 0. The reason I'm writing it is just to compare and contrast with the work energy theorem, which had delta K only kinetic energy change equal work done by gravity, which was external agent. In this new setup, I have extra energy, right? I have UG, and I'm considering the change in total energy on the left, but gravity or Earth is part of the system, so it's no longer external agent, so it's not doing work on the system anymore. So conceptually, this is quite a difference. Does that make sense? So why are we spelling this all out? Well, you have to be careful, so you say don't do double counting, because you can do it either way. You can either do wet and treat Earth as an external agent and do just this, or you can include it in the system and have potential energy, but you can't do both. Right? The object is either in the system, then you have energy, but not work, or it's not in the system, then it does work, but there is no energy associated with that. Is that clear? Okay. So the question is, why do we do this? Why do we want this? Again, think of mathematical convenience. If something is not part of the system, then it does work. What do we need to do to compute work in general? In general, it's actually a pretty tedious task because we do integrals, right? We do integrals, right? And sometimes these integrals are pretty sophisticated. So it's hard to do. Now, what if we switch to the potential energy paradigm? What do we need to do to compute potential energy? Well, you just need to plug and chug, right? You just plug some numbers in the expressions and that's it. No integrals. It's so much nicer. So in fact, it's so nice that you now think, oh, can I actually trade all other forces work to some kind of energy? Right? So what did we do mathematically? Mathematically, we traded work for change in potential energy, right? What is this? It's not exactly change in potential energy, it's negative change in potential energy, right? Because it's initial minus phi. For delta U, you have to have the other way around. So this is negative delta UG. So we traded work for negative delta UG. Okay, so the question is, can we trade work of any force to a negative delta U? And I bet some of you know the answer. We'll trade work of any force for negative delta U. So who knows the answer?
You can.
So not, the answer is no, right? Okay, so then there are two types of forces. Nice forces, whose work is tradable for negative delta U, and not nice forces, right?
Is this like conservative forces? Not
Exactly. Nice is obviously a not official term. The official
So
term,
stuff that won't work is like friction and thermal. No, I forgot the other one. I think
okay,
there's one.
so yeah, well, let's put it down. So two types of forces. Yeah, well, we'll get to the bottom of this. So two types of forces. Potential or conservative. In physics, we usually use the term conservative. In math, they usually use the term potential, but these are synonyms. And non-conservative. And we know like 5 different forces by now, so we can just classify them. Force of gravity is obviously conservative. We just explicitly showed that. And as you probably understand, spring force or elastic force is also like that. Friction is indeed non-conservative. Okay. And we'll understand why it's non-conservative. So if you think about how work is defined, like, let me maybe put it here. So work, which is an integral, right? For U initial minus U final. So if you compute an integral, the result of that integral depends on all the details of the path, right? In general. This expression here does not depend on any path, right? It's some function computed at the initial point and some other, and the same function computed at some final point. Just the difference of two numbers. This has no information about the path, no information about how the particle got from initial to final. So when is this like even possible to replace with this? Only when the integral is so-called path independent. Okay, this is a term. So can do if the work from initial to final is path independent. Okay, and this is actually it. This is a mathematical condition that ensures that type of, like, say, if you're given the force is a function of position and you have no idea where that comes from, how do you know whether it's conservative or not? Well, the criterion is the work path independent? That means if you put any path, then the integral over that path, the work integral over that path is independent of the actual path, right? That's a lot of things to check. However, this condition can be rewritten in a much nicer way, and that's really manageable. You just need to compute a few derivatives, and that tells you whether the given function force is conservative or not. Anyhow, path independence. Tell me if, I'm going to put it here, if the path is closed. Everybody understand what closed means mathematically? It means it's a loop. Okay, so initial and final are the same. Okay, what is the work done by conservative force?
0.
0. Can you elaborate?
Okay, so with the conservative force, you can always say like the potential energy at any point is like a function of its position, right? With respect to the work.
Okay, so yeah, let me kind of explain here. We're not, so this consideration is before you introduce the concept of potential energy, right? Because you're trying to figure out whether it's possible. You cannot appeal to any properties of potential energy yet. Try to use this. Try to work with this definition of conservative force. So you know, for a conservative force, the work is path independent. Can you argue that that means that the work of conservative force for any closed path is always 0?
So like you do like work WII is equal to UI minus UI is equal to 0.
You cannot use this.
All right.
Once again, you cannot use use. You can only use this pink stuff or purple stuff. U comes into play once you establish this. Okay? We're not there yet. It's actually much simpler, folks. So if the path is closed, what is the simplest closed path? 0 path, not going anywhere. Okay? So then work is 0 for no path. Yeah. If consider no path, you're just not going, that integral is trivially 0. But we know that for conservative force, the shape of the path doesn't matter as long as it connects the same 2 points. Okay? So conservative forces have to do the same exact work over this path as over 0 path. Okay. Do the same. Oh, sorry. Same for I equal final. Okay. That proves that closed paths are like no paths for conservative forces. Think about it, gravity. When the object is falling down, gravity does positive work. If you lift the object back up, gravity would do negative work, exactly the same in opposite amount. Does that make sense? Yeah, I think we didn't talk about one feature of the dot product.
Wait, Dr. Kagan, so work is only equal to negative delta U when it's a conservative force, but it's always like it's always true that F is equal to negative du dt, right?
No, only when U exists. If U exists, then yes.
Yeah.
But for some forces, U doesn't exist.
Okay.
So if you already got the U, then of course that means it exists, and you can take derivatives and compute the corresponding force. But for some forces, it just doesn't exist. For friction, doesn't exist. There is no U for friction. And we'll understand why in a minute. Let's just consider this dot product. So I want to write something down. Work is positive if the force is in the same direction, or more or less in the same direction. Or actually, if the angle theta is from 0 to 90 degrees. Okay, the work is 0 if theta is 90 degrees. And the work is negative if the angle is between 90 and 180. That is, the force and displacement are opposite to one, or almost opposite to one another. Okay? Does that make sense? So this is why when you lift the apple and displacement is up, but force of gravity is down, so the opposite, gravity does negative work. And if you lift it by exactly the same distance as it originally fell, clearly the amount of work that gravity does in the two cases is equal and opposite. So overall work done by gravity is 0. Is that clear? Now think about friction. Think about friction. Let's say you move the block across the table. So this is initial. This is final. Force of friction is acting backward. The displacement is forward. So the opposite to one another. The work is negative. But now think about moving this block back from right to left. This is initial. This is final. Can you tell me whether the work is positive or negative?
Negative.
Does everybody see that? So over this closed path, if you move it from initial to the right and back to the initial, overall work, is it 0?
No, it's not 0, which is
No,
why
it's
it's
right.
not conservative.
All right. So it's doubly negative, right? Or if you consider moving a block, let's say imagine it's top view. So if you move a block along a square, a conservative force would have done 0 work. But if it's friction, it actually does quadruply negative work. Right? On every interval, it's always against displacement, so it's always negative work. Okay? That's why friction is not conservative. It does non-zero work on a closed path. Or in other words, the work is path dependent, because it makes a difference if you get from point A to B directly, or let's say along some longer path. The work done by friction will be different. That's what makes it path dependent and non-conservative. Are you all good on this? Okay. Now, let's say what happens to the other two forces that you know, normal and tension. What kind of forces are they? Hmm? So let's say you have a normal force table and a block, and you move it like this. This is the displacement. This is normal force. What is the work done by normal force?
0.
0. Yeah, we kind of briefly discussed it, but folks, I want everybody to be on the same page, especially the new people, right, who were not with us in the spring. So this is because normal force is perpendicular to displacement, and if you think of the dot product is 0. Tension does the same thing, actually. So let me just put it this way. Same with tension. Tension would normally do 0 work, except for when you stretch or compress the string or spring. But if, say, you have an object that swings, then the force of tension is always perpendicular to instantaneous displacement. So unlike this example, tension actually varies in both strength and direction. But what is true is that it's always perpendicular to the displacement, because displacement is tangential and tension is radial. Okay, so you can say work done by tension is 0 because the force of tension is perpendicular to ds, every elementary displacement vector, but that means it always does 0 work. Okay, so these two forces don't really need to be classified, and that kind of completes the list. We had gravity, spring force and friction, and tension and normal force. Okay. Well, let's see how things work out. I'm gonna set up a strategy, problem solving strategy. Probably I'm gonna type. There are 3 steps. So step 1, identify your system. So decide what you want to include in the system. Among other things, this determines the energy content. It determines which types of energy are relevant. Step number 2, consider the right-hand side of the energy balance equation. So this is energy balance equation. Actually, wait, I still need to state that. My bad. Okay. Let me explain what energy balance equation is. Yeah, this was supposed to be here. So I'll come back to this strategy. Let me explain energy balance equation. So you start with wet. That says delta K equals work by external agents. But now let's say you have multiple agents doing the work. So you can say work 1 plus work 2 plus work 3 and so on. Okay, all these external agents. Now, some of them are conservative, some of them are not. So what we want to do, we want to trade all conservative works for negative delta U. And let's say we've traded 1 and 2. 1 and 2 were conservative and the rest were not. So we traded work 1 for negative delta U1 and work 2 for negative delta, delta U2. Okay, so we're going to carry them over to the left hand side. What do we have? We have delta of K plus U1 plus U2 and then so on, however many you've been able to trade. What is left on the right hand side? We have work done by non-conservative forces, plus you may have some remaining external agents that for some reason you did not want to include in the system. Okay, so we'll just label that as W external. Okay, now this is your old friend total mechanical energy. So if you rewrite this, you have total delta E equal work done by non-conservative forces plus work done by external forces. Again, what may be here, say practically, may be like normal force that we know does zero work almost all the time. So why bother? Let's keep it external, and that's where it shows up. The work done by non-conservative forces is the work done by friction, air resistance, drag forces like that. Okay, if you've seen this equation before, put the thumb up. Abhijit, Joseph, Vincent. So Joseph, you haven't. Okay. You have? Vincent, what about you?
Sorry, my background's a bit crowded. Can you restate? My background's really loud.
I asked if you guys have seen this equation in the box.
Oh yeah, the external, internal. Yeah.
Uh-huh. And Vincent and Joseph, what about you? You put thumbs up.
I
So
haven't seen it
you have.
specifically written this way.
Okay. Well, what is the way that's more familiar to you? So you're saying you've seen it written differently?
No, for me, I think I see I work with non-conservative, but like external forces or work is I didn't go into that before. So
Okay. Well, okay, then that's good that we focused on it. Okay. So let's let me finish the strategy. So you start by considering the right-hand side of the energy balance equation. So you need to analyze non-conservative forces, like what kind of work they do, and you also need to analyze the external work. Okay. And if I don't want to say if it's zero, but I want to say if it's under control, because sometimes it maybe is not zero, maybe there is friction. But as long as you know how to compute or how to account for that, you're good. Okay. So if the right-hand side is under control, then proceed to step 3. So in step 3, you consider or expand the left-hand side of the energy balance equation. Okay. And then do the math. So this is really just an equation that relates something in the beginning to something at the end. It's an equation that you can use to work out the math. Does that make sense? Okay, so obviously the strategy per se is not super helpful unless you like apply it to a bunch of problems. So we don't really have time for that, but maybe just quick example, and we'll call it a day. So this is an incline, and you have a block on it that slides down. This is displacement D. The angle is theta. Given the mass, whatever you may need, mass, D, theta, G, and let's say V initial is 0, starts from rest. And let's say there is friction here. So mu is given. So it slides over this distance, over this given distance. I want to find V final. Okay. So let me save it, and then I'm gonna erase the derivation. Okay, so let me just illustrate how the strategy works. Step 1, my system is going to be Earth plus block. I don't want to include the ramp in the system. Well, let's understand what's going on first. So what are the forces acting on the block here?
Gravity, friction.
Is that it?
I think.
Also normal from the
Oh yeah, normal.
Okay, here we go. Let's label them all. Gravity,
I guess I
friction.
included normal with friction.
Okay, three forces. Now, as I included Earth in the system, it is now internal, not external, right? Friction has to be included on the right-hand side regardless, because it's non-conservative, doesn't matter internal or external. So friction, we don't really care. But the normal force seems to be external because that's exerted by the ramp, which is not in the system. So you may say, oh, I want to include ramp in the system. Then it will become internal and like I don't need to worry about that. But here is the drawback here. If you include the ramp in the system, you would have to start considering the forces acting on the ramp. And there is some floor or something, and there is a force on the ramp. Okay, so you may actually get stuck there. It's helpful to stop that process early on, to include actually not too many objects in the system. So what is disadvantage of not including the ramp in the system? Well, the force that the ramp exerts, the normal force, would have to be included in here. But we know something about that force, about that work.
The dot product's going to be 0
Yep.
because it's moving. Okay, yeah.
Yeah, and that's exactly the reason why we don't bother to include the ramp in the system, because we know it's going to do 0 work anyway. So, but that's going to be actually step 2. In step 1, remember, there is the second part that determines the energy content. So what's the energy content? The block has kinetic energy, right? And the Earth block system has gravitational potential energy. There are no springs here, so that's it. So we can write that total energy is just UG plus K. Make sense? But now, yes, let's consider the right-hand side of the energy balance equation. And we know that the work external, actually, systematic here. The work by external forces is work done by normal force, which is 0, and that's because normal is perpendicular to displacement. Now, the work done by friction, it is not 0, but let's compute it. What is it?
Mu mg cosine theta d.
Well, let's do it step by step, okay? So we know in order to compute work, first of all, we need to recognize, is it a constant force or not?
Friction?
Yes.
Yeah, I think so, yeah.
Yes, very good. So it's kinetic friction, it's constant force. What is it equal?
Mu mg cosine theta.
First, I'm going to put n, and n is mg cos theta, so yes, we put. Okay, now the work done by friction can be computed by F dot T, right? So
Oh, it's negative.
it's negative. What is the angle between friction and displacement?
Yeah, sorry, it's 180, so it's negative.
Okay, 180. Very good. So that gives us -1, right? Because cosine of 180 is -1. So we put minus F times D, and if we put it all together, we have mu m g d cosine theta. Look, the right-hand side is not 0. Energy is not conserved, but the right-hand side is under control. That means we keep going, okay? So step 3, the left-hand side of EBE, which is delta E. E final minus E initial. And in energy is this combo. So we write UG final plus K final minus UG initial minus K initial. We need to just figure out every single contribution. One additional subtlety with potential energy is that it's actually, it doesn't have an absolute physical meaning. Okay, the way we introduce potential energy, we trade work, which is something tangible, right? It's a fixed amount of joules. We trade it for a change in delta U. So the change in delta U does have physical meaning. However, U itself has some arbitrariness to it. Think about it. What if you added a 5 joules to U, right? It's a different function, right? But when you just get to compute the differences, final minus initial, those 5s just cancel out. So potential energy is defined up to a constant. And it's absolutely arbitrary, okay? So with that said, that physically or practically, that means you can set up a 0 level of potential energy wherever you want. And you want to set it somewhere at an actual position of the block, either in the beginning or at the end, whatever is more convenient. So I'm going to set UG equals 0. And folks, when you work out problems that involve gravitational potential energy, please do me a favor, just put a little bar and put a note like this to tell me where you chose the 0 level of potential energy. So, and it's with respect to that level that we'll need to know the Y, right, or the H, which is not given, right? But you can easily compute that. Anyhow, UG final we set to 0. It's also easy to see that K initial is 0 because the object starts from rest. K final is 1/2 mv final squared. That's exactly the thing we need to find. And this is mgh. Now you tell me what h is.
D sine theta.
D sine theta. So that's it. Now we set delta E equal work done by friction. So we have 1/2 mv final squared minus mgh. Oh, let me actually expand the h, mg d sine theta equal negative mu mg d cos theta.
You can cancel out an m, and then if you move stuff in factor, and then take the square root, you'll get v is equal to the square root of 2gd times sine theta minus mu cosine theta.
Okay, let me maybe put it in here, where I have the space. So v final is root of
2gd times the quantity of, maybe you could simplify this, but sine theta minus mu cosine theta. I don't know if you can simplify that.
No, you can't really.
Yeah. Okay.
But you need to look at this very carefully. Folks, say, as math person, you probably would be very concerned if this whole combo is negative. Can it be negative for some values of mu and theta?
I think so, yeah.
So if the angle is very small, right? If the angle is very small, then sine is close to 0, cosine is close to 1, and whatever mu is, it clearly can be greater than this almost 0 thing, right?
So when it's when sine of theta is less than that, then you just say that v final, well, it wouldn't move because it would never overcome the frictional force.
Okay, I want you to connect that with something we discussed previously. So while I'm writing it down, think about it. So if sine theta is less than mu cos theta, what are we dealing with?
It never overcame the frictional force. And
exactly. Remember we had critical angle.
Yes.
So
Yeah.
when the theta critical, whose tangent was equal mu,
Yeah.
or arctan of mu, if we talk about the angle itself. So what this means is
Oh,
that
yeah. Tan
tangent
theta.
theta is less than mu. That means theta is less than theta critical. And that means that the block is actually not sliding. And if that's the case, then what is V final?
0.
0. Okay, so V final is either 0 or this, whichever is greater. Well, maybe I shouldn't say greater, but when this is well defined, this is the answer. When it's imaginary, the answer is 0. Are we good?
Yeah.
Okay, so this is pretty much it. I know we went over time, so next time we'll probably finish a bit early to compensate. Any questions? No? Okay. I will post the homework that is based primarily on energy and some previous topics. Some problems will include more than one topic. Okay, and the soft deadline will be Sunday night. The hard deadline will be Wednesday night.
All right.
Okay.
Have a good day.
You too. Bye-bye.